Okay, so Vivek is going to talk about being energy efficient over a wide dynamic range, and that is quite a challenge. So,
I'd like to thank Jan and Jeff for inviting me to come talk about some of the challenges we face in the general purpose computing design, general purpose microprocessor design for getting energy efficiency. It's really important, as we all know today. We have the unique challenge of not only designing for a point optimization, where you want a particular performance, a particular energy efficiency, which is relatively easier, but you want the same design to span a large operating range, which that's what I mean by dynamic operating range. And many of the choices you make in your design can sometimes help your operating range, and which are good. But sometimes you have to make very careful trade-offs that you're not limiting your performance range, operating range, by focusing too much on energy efficiency on one side. So just to summarize the challenge we face, we have to design as few components as possible to be cost efficient, to span a large range of applications or platforms. So you have server, which is 100 watts plus kind of operating thermal power. On the other end, we have handheld devices, which are a few hundred milliwatts, and need to have as few designs as possible to span this entire power range, the entire platform cooling range that you have, all the way from active cooling to passive fanless cooling, the voltage power delivery range that you have, which is wide within a segment itself, the ambient operating conditions you have that can vary from very controlled ambient to extreme conditions. And then we have a variety of workloads that not only vary dramatically across segments, but even within a segment, they vary quite dramatically. So for example, for servers, we want throughput-oriented, parallel transaction processing kind of applications to run well. In the client, we care about both burst mode responsive performance. We care about single thread performance as well as multi-thread performance. We care about graphics, video, streaming workloads. So the variety of applications, and the processor has to really provide this kind of the required performances with minimum energy consumption possible at each operating point. And that's quite a challenge in terms of design, because you have to have a wide range of voltage frequency operations. And of course, you use a different number of cores depending on what segment you're in, and even different types of cores depending on what segment you're targeting. So the challenge here is that you have to have as few designs as possible, so you can scale across these segments in a cost-efficient way. And you want to have a modular design, so you can mix and match stuff to span within a segment all the requirements that you have in a quick and efficient way. So given that background, I'll talk about some of the future platform characteristics that we'll have. We'll see more and more in our Intel platforms. The first is that we'll have a lot more of dynamic platform power control. So if you look at our future single chip or multi-chip package designs, you have a variety of components in there, not just a single microprocessor. You have the cores, you have the cache, different cache levels in the hierarchy. You have on-die interconnect fabric, where different things plug in, which is scalable. You have some accelerators like graphics and video, special purpose engines like for encryption. You have memory controllers integrated on the same die, and off-die interconnect support. Now, for a variety of workloads, your goal is to really provide the best user experience while consuming minimum energy. So the focus is going to go away from frequency, performance at an architectural level, but to really talk about a user experience that you need. And you need to provide that with minimum power consumption, minimum energy consumption. So to enable that on the design side, you need to have independent voltage frequency control regions, because all these components at different points of time need to have the choice of being able to operate at the optimal voltage frequency condition to provide the experience you need. You need to have scenario-based power budget allocation. So you have a certain thermal power budget for this chip, and you want to shuttle that around. You want to shuttle the budget around based on what's running. For example, a graphics-intensive workload should shut down the core as much as possible and allocate the entire power to the graphics. So those features need to be there in the design so that the platform layers, the platform components can exploit that to provide the dynamic capability. Of course, you need to have dynamic voltage frequency control and shutdown and activation very efficiently so that you can adjust to user scenarios and workloads. We also need to worry about dynamic adaptation, because typically we set our operating conditions based on the worst possible case, because we don't want to violate any guarantees or violate any user expectations, right? But that's because we don't have any dynamic mechanism to adapt to changing environments, changing workloads on the fly in an efficient way to really not pay the penalty of being in the worst case all the time, because the worst case arises very infrequently in many cases, and be able to exploit the margin that you have for either energy efficiency or performance. So you can think of a processor having different components, and there are sensors in the processor for sensing environmental changes like temperature, voltage droops or voltage changes, changes in activity levels by supply current sensors, changes in degradation of the processor over lifetime due to stress, so-called aging. And those sensors feed back to a dynamic control unit, which can, on the fly, adjust voltage and frequency in the right way to really make sure that you're not worst-casing your settings. Also, you can reconfigure the components in a way that's optimal for a usage scenario or a workload, depending on what's happening. So I think adapt and reconfigure for the best power performance at any point of time during the operational lifetime of the processor will be key going forward to really improve energy efficiency and at the same time not give up on performance. So resiliency or error detection correction has been widely used in servers, as we know, high-end enterprise-class servers to improve reliability, soft errors or infrequent errors. There's some work recently going on to really apply that to improve energy efficiency and performance by basically pushing the voltages and frequencies beyond the point where some errors occur due to timing failures, and then having mechanisms for detecting them and correcting for them, so that as long as those errors are infrequent enough and the recovery mechanisms are, the overheads are low enough, that you can maybe get some benefits in energy efficiency and performance by pushing the envelopes of voltage and frequency. So a resilient platform framework used for reliability or for energy efficiency improvement will have detection mechanisms for diagnosis, confinement, correction mechanisms for the error, and then system recovery and adaptation depending on changing environments, and then configuring the system differently if needed. So you have to implement these things at different levels in the layers of the platform. So maybe the error detection can happen at the microarchitecture and circuit level, and then some of the recovery, corrections, and adaptations can happen at the system software layers, and then the application and programming systems can guide the adaptations and the reconfigurations as the need be. So if you implement these mechanisms for error correction and detection at a lower level in this hierarchy, you can respond faster, you can detect errors at a finer granularity, but you have a larger complexity to deal with at a lower level to recover and to correct for the errors. And as you go up in the level of the hierarchies, you have less and less errors, because a lot of the errors that show up at a low level don't really manifest themselves at a system level or at a higher level because they're not relevant for the data being run or the program being run. So you have a effectively masking of errors as you go up, and effectively much lower error rate, and which affords you a larger recovery time or a larger recovery overhead, which you can manage in that framework. So the goal is to really have an optimal implementation of these error detection and correction features across these different layers in such a way that you're taking advantage of the capabilities of each layer going forward. So beyond improving reliability, which has traditionally been the use of resilient platforms, I think in the future there will be some applications of this to improve the efficiency and performance as well. So idle power is bad, standby power is bad. We all established that this morning. Even within sort of a so-called active operation from a chip designer point of view, from a microprocessor chip point of view, today we have the OS monitoring the load, sort of a 15 millisecond kind of ticks, right? So wake up and you shut down on 15 milliseconds. That's too long, because you can waste a lot of power in 15 milliseconds if you're not doing anything for a CPU. So we are limited by the workload monitoring part. We are limited by how fast we can change voltage frequencies, how fast we can change states, and that's where we are today. So going forward, we need to remove all this wasted energy. So even during the 15 millisecond period, there are opportunities to shut down and respond to finer demands in time scale to changes in the performance demand or the workload. And some of the enablers for that will be ways to find faster ways to change voltage and frequency, ways to reduce the latencies for getting in and out of active and sleep states, predicting wake up, because you can improve the performance penalty by waking up early a little bit. If you know, you can do that. The state transition energy, because a lot of the limits to how fast or how effective it is to wake up and go back to sleep quickly depends on how much energy you spend in the transition. So the more energy you spend in the transition, so less effectively you can respond to changing workloads. And of course, when you do all of this, you create a lot of supply noise. To change voltages fast, you remove a lot of capacitances, which hurts your voltage droops, and there's a tricky balance to be played there to make sure that we are doing these things the right way. And there's a lot of research going on and development work going on to make a finer grain voltage frequency and state transition possible in the CPU for our future platforms. Of course, you want to do it on a spatial domain also. Often today, all the cores share the same voltage and frequency, which is not the right thing, because when you're running a heterogeneous workload, some cores could be shutting down, or some cores could be running slower, others could be running faster without impacting user experience. So you want to have ideally each core and cluster running at its optimum voltage and frequency, and even going even below within a core or within the platform itself, we want to do more of that. So the circuit challenges are you have to have efficient translation or conversion circuits across voltage frequency domains. You have to make sure the synchronization latencies are tolerable across crossing frequency domains. You have to distribute multiple clocks, multiple power grids on chip, and then in package. Some of those things are challenging from a design point of view. But more and more of that will happen, I believe, because there's no other alternative around those. One of the key enablers on the efficiency of the packaged microprocessor is the amount of energy you lose in the voltage regulator. And clearly, this is much more severe for data centers, and if you look at the entire data center power delivery distribution. But even for a client, laptop, or even desktop microprocessor, the voltage regulator eats away a big chunk of your energy budget. So one of the ways to address that is really not only make them more efficient, but make them smaller. And the way to make them smaller is make them higher frequency VRs. And higher frequency VRs, when you're converting from high to low voltage, are really inefficient because of switching losses. You need better devices, which can tolerate high voltage and give you good resistance at the same time. But to really shrink the VR and the microprocessor combination, there's no other choice but to bring some part of the VR as close to the point of consumption of the load as possible. And so efficient, area efficient, and power efficient VRs is definitely key, and integration of the VR as close to the processor certainly is a way to do that. It also helps with your distribution losses, because you're converting from high current to low current to high current as close to the point of consumption as possible. You're reducing the parasitics in the distribution to get a better fidelity of the supply. And of course, you have a better control of ramping the voltage up and down. So a prototype in our lab that we built, which has in the same board, the same package actually, we have the converter chip and the load chip, and we have under the cavity, we have air core inductors. Of course, you can do better than that. But that showed that you can operate at 60 megahertz kind of frequencies, get reasonably good efficiency. Not as high as our 12-volt VRs that have 90%, 95% kind of efficiencies. But going to higher frequencies definitely helps to reduce the size, get rid of a lot of decoupling caps, make the inductor component smaller. And the efficiencies are reasonable, but obviously you can work more on it and do better. Other key aspect of a wide range operating VR is that you need to worry about efficiency across the entire current load range, not just your typical operating point. So you need to configure the VR appropriately for low load situations where you have a lot of DC and switching losses. And then, of course, for the high load, where you have conduction loss dominating and have a lot of transient supply noise, you need to make sure the VR is configured to respond to that. So this is a step towards VR innovations that I think will be critical for improving the overall energy efficiency of your platforms. I want to talk about a multi-core, many-core research test chip. Parallelism is the way to go forward to improve energy efficiency, as Mark mentioned. And this was our sort of a research chip to get some understanding of what it takes to design sort of an 80-core, even though small cores, machine with some kind of interconnect fabric. Each tile in this had 2 floating-point multiplier accumulator units, some IMEM and DMEM register file, a crossbar router for connecting to east, west, north, south to itself, and also upwards to a 3D stacked SRAM, which of course is costly, but one of the ways we wanted to investigate to reduce memory bandwidth power is to see having another level of large cache between the main memory, and this can reduce your I/O and memory power. So this operated at 5 gigahertz, give you about a teraflops, more than a teraflops under 60 watts, so it's a pretty big chip. The global clock distribution was sort of a differential low voltage, and we could handle about a cycle of clock skew between tiles. We had a asynchronous communication scheme among the tiles, and that helped reduce the clock power quite a bit. We also had a lot of fine-grained power management within the tiles as well as between the tiles to really shut down tiles and activate tiles as needed. We had 21 different regions of sleep within the tile, which they could be activated, deactivated. Either you can lose the data value, shut it off, or you can retain data depending on what you want to do, how soon you want to wake up. And all of these techniques allows us to get in the lab about 19 gigaflops per watt kind of energy efficiency in 65 nanometer CMOS. Going to external memory, especially when you have 80-core chip operating at teraflops per second, you need to get significant memory bandwidth to feed the engine. And one of the ways we want to address that, you have a large cache memory, which cannot be on die because the die is already too big, so 3D stack it on top of the die. And by doing that, you reduce the bandwidth pressure on the external memory. At the same time, you get a lot of, the 3D stacking gives you a lot of very short and dense interconnections that you can drive at relatively low frequencies to be efficient, and at the same time get a high aggregate bandwidth. And using through silicon vias, you can connect to the off-chip package, and so that was an experiment we had done, and we are going through some of the testing in the lab. Now I want to switch a little bit to the wide dynamic range problem. So you want to operate as fast as possible when you need to, and what limits you there is the Vmax, reliability of the transistors, the interconnect current densities, both on chip and at the die package interface. And often when you want to go to low frequencies, you want to reduce the voltage as much as possible to support that frequency. And there the limits come from circuit failures due to noise and SRAM stability and so on. You have soft error issues. And eventually you have a steep frequency roll-off, where even if you slow down the frequency by 10x, you can get like 10 millivolts change in voltage that you allowed because the frequency started rolling off. And there the steep subthreshold slope devices clearly is a way to go for getting below that limit without compromising performance at the high end if you can manage that. And then of course aging also degrades the Vmin that you can support. So if you look at the problem of margins that we build in to guarantee error-free operation, we have a margin for voltage variations to all sorts of supply noises. We have temperature variation margins. We have aging margins. And by doing that, you're really subjecting all processors to the same margin, even though the history of each processor will be different in the lifetime of its usage. And so you can't exploit that if you build in an upfront margin for that. And then you have margin due to delay variations and path switching activations that happen depending on the workload. So we would like to remove these margins as much as possible across the entire range of voltage and frequency, not just a single point. To get around the Vmin problem, the main limiter for that is the large SRAM die that you have, a large SRAM cache that you have on die. And you have the bits failing due to within die variations, and the worst die is obviously, it's even more limiting. And then you have soft error, erratic bits, aging, and supply noises all combined to make the Vmin really, to get below a volt or below 0.5 volts, substantially challenging. So even the typical transistor, you can do it, but for integrated small bits, it's very hard. So look at the Vmin versus density design space for SRAMs, and you find that for 60 SRAM, if you can give up density, make the cells bigger to reduce variations, allow better ratioing of transistors, you soon reach a Vmin limit, and you can have to make it 10x bigger at some point to get like 10 millivolts of Vmin improvement. By using multi-voltage SRAM, you can, for the same density, you can perhaps get some Vmin improvement. But if you really want low Vmin, you have to eventually move to a 8T or larger number of transistors in the cell to decouple read and write stability, and then so you can get a better Vmin on a different trajectory here. Of course, the density loss is quite dramatic, and but depending on what kind of cache that you're looking at in the chip, the first level cache or the last level cache, you can make the right choice there. One of the ways to decouple the cache Vmin problem from the core Vmin problem is to really separate the cache and put it on a separate power rail. And so the cache is on its own power rail, which has its own smallest bit cell, a high voltage that doesn't exceed the Vmax, and the core can now free to go up and down in voltage as it needs to. And we have done that, and we have embedded level shifters to really do that in a sort of a less low overhead way, so that communicate the core and the cache communication doesn't suffer too much. You can use a dynamic multi-voltage cache. So if you look at a 60 SRAM cell design, you have a conflicting requirement for transistor sizing. So the NMOS needs to be strong for write, but weak for read. The PMOS pull-up needs to be strong for read and weak for write. So how you satisfy both? You can do some extent. To some extent, you can do that using transistor sizing, ratioing, and process targeting. But to give you a more flexible way of designing an SRAM cell, and you can really want to use voltage as your knob. So during read, you want to use a low voltage on the word line to make the NMOS weaker. And during write, you want to collapse your supply along the column to make sure that the PMOS is weak enough for you to write properly without losing the data in the other cells in the column. And we did a test chip where we found that you can do a dynamic multi-voltage and make a minimum size cell work where all transistors are the same size in the cell by proper settings of the word line voltage and the bit line and the collapse voltage. You have to worry about supply noises, differential noises between the supply of the word line and the cell supply, to worry about variations of these pulses when you're collapsing the voltage. But those can be handled by some of the tracking circuitry that's built around this chip to make sure those are robust enough. When you go to low frequency mode, your DRAM looks much closer in terms of number of clock cycles. So you can live with a fewer or smaller cache size without giving up too much performance. So, and low frequency mode, you're limited in voltage scaling with the cache. So if you reduce the cache size, then you can scale the voltage a little further when you get into low frequency without really impacting the architectural performance. So some of the ideas here are that disabling ways or banks or subarrays or bits or even words to really, when you get into low voltage mode, disable some of those things that fail at low voltage and live with a smaller amount of cache. And when you do that, the results are quite significant. So if you just disable defective words or defective bits at low voltage with some overhead, of course, in mapping and testing and storing this information, you can find that you can get a little loss in IPC, instructions per cycle, but a significant gain in Vmin as well as energy per instruction. So that sort of looks like a fair trade-off to make when you go to low frequency, low voltage modes. How long do I have? 2 minutes, okay. Wrong question to ask. Now once you've solved the cache problem, then you have to worry about the logic. Eventually, the logic is going to fail at low voltages. Clearly, some of the known techniques of limiting the fan-in. You don't want to have wide, leaky transistors, degrading ion on IF ratios at low voltage. You don't want to have install stacks of transistors which degrade significantly at low voltage because of body effect and gate overdrive loss. You want to have flip-flops which are robust, size your keepers properly, make sure all the worst-case conditions are met in your device variabilities when you do that. You have to worry about level translators. So when you have multi-voltage designs, often the level translators fail. And we have the designs very robust, but you haven't paid enough attention to the translators. And the level translators fail because the input voltage goes too low, and the PMOS becomes too strong, and then you have a contention issue. And you have to, the split level converter topology shown here decouples the driver PMOS from the cross-coupled PMOS and allows you to size them more independently and better to really provide a low robust level converter. So a lot of these choices you make, as I talked about, they sometimes, for example, dynamic platform control. You shut down things when they're not active. That improves your active energy budget of the remaining components. So that helps your operating range. But some of the choices like bigger SRAM cells or low fan-in gates, they do compromise to some extent the Fmax side of things, right? Because you have lower power budget, less frequency, you can get on the higher side. So you have to really balance them carefully. An example, a domino versus static CMOS. Domino CMOS is great for Fmax, high frequency, but if you want a wide range, robust design, static CMOS is better. So these choices have to be made very carefully depending on the specific situation so that you're balancing both the energy efficiency that you need, but also make sure that you're not compromising on the range. An example of a low voltage motion estimation engine that we built in our lab, it operated up to 240 millivolts. But the energy efficiency best point was 320 millivolts, so there's no reason to go to sub-thresholds as far as we could see. We could live pretty much with near threshold or little above threshold. Clearly depends on the leakage and the activities that you have. But getting to 200 millivolts or so is pretty challenging. And we can do it in the lab for a single chip with a few 100,000 transistors, but pulling this off for a multi-million transistors to be quite challenging. But there are design techniques that you can employ to make the things more robust. Some results in dynamic adaptation to voltage and frequency variation. We built a processor which has thermal sensors, droop sensors. It's a voltage, droops, the frequency changes to track the droop. And the droops are infrequent, so you can adapt to them quickly. And you can do the same thing for aging degradation. Quickly want to cover resilient circuits, as I talked about. There's a circuits test chip we built which has error detection flip-flops and mechanisms for feeding that back for error correction. Some of this work was started in University of Michigan, the RAZOR program, where they first implemented this kind of technique. We are looking at further improvements or implementations of that to see how we can make it work in a microprocessor. Some examples from this test chip that it works, and you can get significant gains in power or throughput depending on how you use it. And that's my summary. So in the interest of time, I leave it for Q&A.
Thank you. That was very interesting. And I'm trying to interpret the title, Why Dynamic Range? Did you mean the dynamic range and using a lot of power and using very, very little power? Is that the sense?
Frequency and power range.
Okay.
During active operation, yes.
Any questions? Go ahead, Mark.
So just one question. You're talking about doing adaptive voltage independently for the different cores or different sections. So that means you have to distribute many different power supplies onto the die. And from what I've heard, one of the bigger issues is the cost of the package and the fidelity of the power distribution through the package. So is there some new technology? How do you think that's going to get resolved?
Yeah, the short-term challenge in doing that, as you pointed out rightly, is that how do you distribute through the package and the die so many different power rails? But our vision is that there are technologies out there in the lab and some of them in advanced development phase that will allow you to integrate some of the power voltage conversions on die. And there are not hundreds of them on die, clearly, but enough of them on die to make it practical to have a few power rails that are independently controlled. I believe there'll be evolution of such technologies going from inductor-based VRs to maybe switch cap and maybe some combination of linear regulators, since you already have a power gate in your design. So I think a lot of R&D work is going on in figuring out the right trade-offs there to make it practical.
Okay, so in the interest of time and getting to our break, let's continue the discussion during the break, and let's thank Vivek again.